This is a document describing a very small generator which is particularly effective. I have already shown the very impressive 150 watt self-powered 110mm diameter rotor generator designed, built and used daily by the South African developer who has so kindly shared his designs with us. He has continued to advance his designs and test many alternatives. His latest design has a very small rotor of only 48mm in diameter, and it uses only one coil, which both drives the rotor and extracts excess energy, which charges up to 7 12-volt batteries, as well as keeping its own drive battery charged up. It is a very small and compact generator, although the rate of charging is impressive. This is the unit here. You can see the small rotor with 3 sets of magnets in it. Each set of magnets is made up of 5 3mm thick, 20mm diameter ferrite magnets, and they're enclosed in the acrylic rotor with a 2-inch diameter piece of plastic piping, commercial piece. There's the single coil there, and this is the magnetic pickup, which is a Hall effect sensor. This is a very effective device. It's only one coil because 2 coils cause it to rotate so powerfully that the rotor is liable to destroy itself. The rotor is made from a thick piece of acrylic plastic cut into a circular disc on a lathe, and with 3 evenly spaced holes of 20mm diameter drilled in its side, and a length of 2-inch diameter plastic pipe around the outside to contain the magnets which are stacked inside the 20mm holes. The rotor is mounted on a bearing taken from an old disk drive. That's the bearing there, and it's very effective. The rotor has been used in earlier projects, initially with 6 coils. There's the rotor, and the 6 coils are mounted around it. Later it was used with 2 very small coils turned sideways. However, this implementation uses just 1 coil, and that's a coil taken from an old doorbell. The arrangement is very neat and very tiny and extremely small. The wire used in this particular bell coil is 0.3mm in diameter of enameled copper wire, and so winding a similar coil should be quite easy if an old bell coil is not available. The circuitry remains the same as before, and so is very well tested at this point in time. This is the circuit here. You have the rotor itself with the magnets encased inside it. You have the Hall effect sensor picking up the signal when a magnet passes by. This is the coil which both drives the rotor round and collects excess energy. It's driven by an IRF 840 FET transistor, and when that switches off, the excess voltage, which is around 600 volts, gets fed back through those 3 1N 5408 diodes back through a whole string of 7 batteries which are being charged, and as it continues on down through the drive battery, it also charges the drive battery, making this system self-powered. The actual sensor signal is powered up and amplified by, in this case, a 2SC5353 transistor, because that was to hand at the time. The transistor used here can be any high gain, fairly robust transistor, because it's only amplifying a small signal there. The circuit is started by closing this switch here to connect the drive battery and then giving the rotor a spin. This particular A3144E device is a Hall effect sensor, and it triggers when a rotor magnet passes by it. That signal passes into the base of the transistor, switching it on, dropping its collector to 0 volts, cutting off the IRF 840 FET transistor, and so starving the coil of current, which in turn creates a magnetic pulse which drives the rotor on its way. When the FET switches off, its drain pin D rises to a high voltage of around 600 volts. The 3 diodes connected in parallel pass that voltage spike across to the 7, I see it says 3 here, that's wrong, 7 12-volt batteries, causing them to charge very satisfactorily. However, as their charging current also passes through the 12-volt 7 ampere battery driving the circuit, that battery also gets charged. Not so much as the top 3 batteries, as the drive battery is also discharging into the circuit, and that sort of an arrangement never charges as well as a battery which is not also discharging. This design is so effective that it produces 600 volt output spikes even if the rotor is just spun by hand. The IRF 840 FET is a 500 volt 32 amp pulse current transistor. The 2SC5353 transistor is a 700 volt 5 amp pulse current control with a low gain of only 10. It doesn't need to be a power transistor, and that was used because it was to hand. Any high gain transistor with reasonable current handling ability should do, perhaps a TIP 3055. As with almost all free energy devices, the setting up and adjustment makes a major difference. The rotor being so small, it needs to be made very accurately, usually with a lathe or perhaps a 3D printer. The 20mm diameter holes in the rotor each hold 5 ferrite magnets, size 20mm in diameter and 3mm thick. Exactly where the Hall effect sensor is positioned is important, so it is mounted in a way which allows both horizontal and vertical adjustment. Obviously the sensor must not touch the rotor, and surprisingly the gap between the sensor and the rotor can be anything up to 10 millimeters, as that distance does not seem to make any great difference to performance. By contrast, the horizontal and vertical positioning does make a major difference, and the developer describes it this way. He says the magnetic effects of the rotor magnets are shown in this diagram here. The dark grey region in the center is the full magnetic strength, and the light grey area surrounding it shows a reduced magnetic field effect. The vertical position of the sensor determines both the current draw from the drive battery and the rotational speed of the rotor. At the top or bottom positions, that is here on the left or here on the right, those two particular positions give the shortest amount of current draw from the battery. In the center position, the passage of the magnet past the sensor is obviously the longest, and this is a tempting position to use because it results in the most impressive raw power. It is not, however, the best position in most instances. The light grey circle indicates the region of sensitivity to the magnet, which the sensor exhibits. Usually that is about 5 millimeters wide, that particular light grey band. So the sensor can trigger 5 millimeters before the magnet arrives, and it still draws power for 5 minutes after it passes by. This is important. Many folks seem to be very concerned about the radial position of the sensor, and from a scientific point of view it is of course very worthy of close study. However, from a practical consideration, I would advise not to waste too much time on this point. Just use trial and error. Make sure that the Hall sensor mount is adjustable horizontally as well as vertically, and move the sensor into the position which gives you the best results. The rotor is connected to its base by just being a push fit. For that arrangement to work well, the rotor construction has to be very accurate, and the arrangement is like this. The rotor just pushes down onto the bearing. Some rotors have, or should I say some bearings have a vertical bolt which can be used to additionally hold the rotor, but that's not essential and not all rotors have it. The overall unit is actually very small. This is only 50 millimeters across here, so you can see that the entire unit is actually very small. The sensor in this particular arrangement is about 1.5 millimeters away from the rotor, and the coil is on a solid metal core, which, since the core has to magnetize and demagnetize very quickly, that core will be made of iron or its equivalent. Zinc plated iron bolts are readily available, and they work very well and do not hold their magnetism, unlike steel. If you use mild steel for the core on that, it will become permanently magnetized very quickly, in fact almost instantly. That coil anyway is wound with 0.3 millimeter solid copper wire, which is covered with enamel paint for insulation. The distance between the flanges is 15 millimeters, and the width of the winding is 20 millimeters, and the DC resistance of the entire coil is 10.6 ohms. Again, I should like to thank the South African developer for so generously sharing his successful designs with us.